All right. Hi, welcome to Lost at Sea. This is a presentation by me, David Johnson.
And me, Zaid Fackenthal. All right, what are we going to be covering in this presentation? Well, there's this ship, the El Perdido, that is lost at sea, or it has at least lost power. And the U.S. Coast Guard is trying to locate it by sending out three search vessels: an airplane, a helicopter, and another ship, uh, and is trying to find the lost ship based on water currents and the previously known data. At the same time, the captain is also trying to help and find his own position. However, he is basing it off of his velocity and acceleration logs. And at the end of this presentation, we're going to see whether any of the rescue craft locate the lost ship. All right, so our first part we're going to look at is estimating the longitude. This is based on the previously known values given to the U.S. Coast Guard of the ship's position and velocity. And by plugging in these points into the graph and following the slope lines, we're able to see what course of action the ship, which is C3, the helicopter D2, and the airplane S1 are going to take. If you look at the graph, the airplane is significantly far off from the converging value that the helicopter and the ship are taking. And whether either of them are going to find it, we don't know for sure, but you can notice that the airplane is going against the current and the slope field.
All right, cool. So on this slide, we're estimating latitude, and for this one, we also have to calculate our own data points, and we're going to use Euler's method for that, where we're looking at effectively it's the equation you can see on the screen now, but it's effectively looking at the predicted path of the
ship or the
ship. Words,
vessel.
wow. Yeah. Okay, it's working off of the previous location and where we think it is going. And then based on the time intervals, that'll change how it's drawn and how it looks. This is a version of a numerical solution, which is a way of estimating and approximating how the data will behave. It isn't the actual data, but it's a prediction of where it is going and how it will work. These values can be more or less accurate based on the delta t interval as well. That's change in time. So yeah, we take the data, we plot it on the line, we plot it on the graph. Ta-da, you have S1. We use the same method for D2 and C3 that we did on the previous longitude test thing, the lines, basing it off of 0.4 days per step for D2 and 0.2 days for C3. Both of those lines are based off of the slope field estimation method, which is literally just following the lines and following where it's pointing and just drawing lines at every interval. This is basically the same thing as doing a numerical solution, at least in this instance, because they're both more or less accurate based on what your delta t is and how all of that plays together.
One more thing I would like to add is that, as he said, with the helicopter and the ship, those are smaller time intervals. So based on intuition, we can kind of see how they follow the slope field better. While the airplane, the S1, is more jumping around a bit, and that's because its time interval is larger. In order to get a more accurate numerical solution, not only could we decrease the amount of time, but we could also check the surrounding data points to see if it makes sense. That's when we're looking at the airplane, we can see how it's jumping over the place, and that kind of triggers us thinking, hey, is that correct?
Cool. Yep.
All right, this is our comparison of our datas. We took our estimated longitude values and our latitude values for the three search vessels and calculated their points on the left and in the graph on the right on an XY plane. As you could see, the airplane is significantly farther away from the boat and the helicopter. And we'll find out later, if you ignore the values down there, whether any of them do find the lost ship.
Cool. All right, so now we're going to talk about Euler's dead reckoning. This is a method used by Captain Gomez, in the story at least, where he takes his known velocity and his known acceleration to estimate his position. How we got our formula was we had our formula, we used it. Words, that was wrong, but whatever. We have a formula, okay. Now, luckily, we don't actually have to take the limit of our formula because we can just kind of use a smaller delta t. That's really all we're doing with that limit. So if we use a smaller delta t, there's no limit that's needed to be taken, which is great. Very nice, very useful for not suffering through math. Yes, all right. Euler's method effectively asks the question of, just breaking down what Euler's method is. It effectively asks the question of, 1, where am I now? And 2, based on X amount of time later, that's our delta t, where will I be? This is assuming that the direction the item we're looking at started moving in is the same it will be at the next time interval. Just constant slope, effectively.
Yep.
Now, this is how we actually calculated our numerical data points. We took the x prime and plugged it in and calculated xk. Technically xk1, but whatever. And then we plotted it on the graph off to the side, and that's what you see. You see our numbers: the 0, 0, negative 0.5, 1, negative 1.5, 2, negative 3, 2. That's all.
This is all to estimate where our end position is based on our velocity data.
That's the words.
From the ship's perspective for Captain Gomez. If we look at the next slide, we're actually going to look at Taylor's dead reckoning, because this is when the captain thinks, hey, I might get a more accurate result if I take this formula, this method, which actually takes into account my acceleration, because I have that data. If you look at the formula down below, that is just the Taylor's method, and we have the value of our previous position, our change in time multiplied by our velocity, and our change in time squared divided by 2 times our acceleration. And when we calculate those values using plugging them in, as he went over in the last slide, we get a new estimate for the captain that we assume is more accurate into his actual position at negative 3.52.
Cool. So our general findings. This was kind of spoiled earlier in the presentation, but nah. So yeah, our general findings are, of course, S1 is nowhere close. It is miles away from everything else, and based off what we did in the last slide with the Taylor dead reckoning and all of that, El Perdido is not even remotely in the same realm as S1. Now D2 and C3 are both a lot closer at half a mile away. But unfortunately, only D2 is able to spot El Perdido because C3's search radius is not big enough. And
yeah, that is our presentation. As you found out, our helicopter was able to locate the ship, and this is our presentation. Thank you for listening. Psych, we're not done. We need to check our data with D field. Okay, so the first thing we're going to look at is longitude. I believe this is longitude.
Yep.
Where the purple line is the exact.
So it's the Dormant Prince adaptive step.
Correct. In order to estimating position. While you can see the other 2 red lines, the airplane one you can definitely see jumping all over the place. So we were accurate in our method in finding that then, while the ship and the helicopter are closely following the actual path. If we look at then in latitude,
got it.
Latitude, I will keep talking while he puts up the next ones. But the purple line is our estimate. Is our estimate for? We're good. Is the estimate for?
Got it. There we go. We're good now.
Using again the adaptive step, trying to follow the path, while the following red lines are the ones that are again the ship, the helicopter, and the airplane. The airplane one's jumping all over the place, while the helicopter and the ship, again, more closely follow the actual path. All right, now thank you for listening.
Yep.
Double psych. You thought we were done. No, there's one last thing we need to get to about our math ships. This is our spreadsheet we have for calculating our TDR and EDR, Euler's method and Taylor's method for finding our ship. Based from the captain's data, we have our time, we have our calculated value, we have our velocity, we have our acceleration. The top one is EDR, the bottom is TDR. An example, this is how we check to make sure our answers were correct. For example, for this here, we have 0.5 is equal to the initial condition, our first position, plus our velocity times a change in time of 1, plus our acceleration divided by 2 times our change in time, which is also 1. There we go. Now, really, thank you for listening.